For 50 years, the plan for surviving Yellowstone rested on a single promise. We would see it coming. A giant chamber of magma slowly filling over centuries, a warning impossible to miss. A study just published in the journal Science says that picture is wrong from top to bottom. There is no lake of lava under Wyoming. There never was. The heat arrives sideways, riding a current of solid rock researchers are calling a mantle wind. The magma sits locked in a crystal mush that cannot erupt as it is, and the liquid eruptible kind appears to assemble only shortly before an eruption itself. Which leaves the question the scientists behind this work are now living with. If the warning sign we were all told to watch for does not exist, what does the real warning look like? And would anyone recognize it in time? One thing before we get into it. If you enjoy what we do here at Project Nightwatch, hit like and subscribe so you don't miss the next debrief, and leave a comment with where you're tuning in from tonight. Now let's break this down. Part 1. The diagram was wrong. For 50 years, every textbook agreed on what was under Yellowstone. There was a picture, and you have seen it, whether you remember seeing it or not. A cutaway of the Earth. A red column rising from somewhere near the planet's core, punching upward through thousands of kilometers of rock like a torch flame, spreading into a bulbous head directly beneath Wyoming. That column had a name, the mantle plume, and it appeared in museum displays, in documentaries and classroom posters, in every animated explainer ever produced about the most famous volcano in America. It was the anchor of the entire story. It was the reason Yellowstone existed. In April of 2026, a team of researchers published the most detailed three-dimensional model ever built of what is actually underneath the western United States. They simulated the rigid outer shell of the planet and the slow, flowing rock beneath it, all at once as a single physical system, and they let the whole thing run according to present-day physics. Then they looked for the column. It was not there. Let me say that again, because it is the single most important sentence you will hear tonight. The column at the center of every Yellowstone diagram you have ever seen, the towering red chimney rising from the planet's interior, does not appear in the best model anyone has ever constructed of this region. The team searched the simulation for the buried source that 50 years of textbooks promised, and the simulation handed back something else entirely. The heat-feeding Yellowstone is not rising from below, it is arriving sideways, and the place where the melting actually happens is not thousands of kilometers down near the core. It is shallow, startlingly shallow, a lot closer to your feet than anyone ever drew it. The study came out of the Institute of Geology and Geophysics at the Chinese Academy of Sciences, from a team led by researchers Cao and Liu, and it was published on April 9, 2026, in the journal Science, one of the two most scrutinized scientific venues on the planet. This was not a blog post or a press release. It went through peer review at the highest level, and its predictions were checked against 3 completely independent lines of real-world evidence: seismic imaging of the region, the chemistry of the rocks that Yellowstone has actually erupted, and precise measurements of Earth's gravity field across the western United States. The model matched all 3. Regular viewers might remember that we flagged this study back in April, in our video from April 15th, when the paper first landed. That night we gave you the headline: "The plumbing under Yellowstone had been redrawn, and the old chamber picture was in trouble." But we also left a question hanging at the end of that video, and I told you we would come back to it. The question was this: if the Great Column is gone, what actually generates the molten rock under Yellowstone in the first place? What melts it? Tonight, we go all the way down. The full answer is now on the table, and it is stranger than the theory it replaced. Here is why this matters beyond scientific bookkeeping. Yellowstone is arguably the most monitored patch of ground on Earth. It has more seismometers per square mile, more GPS stations, more temperature sensors, more published papers than almost any other geological feature anywhere. Around 4 million people walk through it every year, taking pictures of elk and bison and boardwalk pools, most of them never realizing what the ground they are standing on has done before. And that ground has produced 3 caldera-forming eruptions in the past 2.1 million years, events so large that the biggest of them belongs to a category with only about 20 members on the entire planet. The behavior of a volcano's next act depends on its source. That is not a slogan. It is the foundation of every forecast, every hazard map, every emergency plan. You model what the system will do next based on what feeds it, how it is fed, and where the material sits. And we just found out that we had the source wrong. Not slightly wrong. Wrong in direction. We have the heat going up, it goes sideways, which means every model of a future Yellowstone eruption, every scenario the agencies have gamed out, every precursor checklist, every assumption about how much warning the instruments would give us, was built on plumbing that does not exist. The researchers' own framing, repeated across the coverage of this paper, comes down to a single admission. The plumbing is different than we thought. Sit with how unusual it is to hear that sentence about this particular volcano. Not about some obscure seamount in the Southern Ocean that 3 people study. About Yellowstone, the system with its own federal observatory, its own dedicated monitoring network, its own shelf of dissertations. When the people who know a machine best tell you they had the wiring wrong, the correct response is not panic. The correct response is to ask what else was resting on the old wiring diagram, and the answer, in this case, is nearly everything. The eruption scenarios, the hazard assessments, and above all the assumptions about what the early warning of a real crisis would look like. That last one is where tonight's story is ultimately headed. That is what this video is about. Not a prediction of doom. I want to be clear from the start that nothing in this new work says an eruption is coming, and the researchers themselves are explicit about that. What this study destabilizes is something quieter and, in a way, more uncomfortable: our confidence. The most studied volcanic system on the planet had its basic wiring diagram wrong for half a century, and the scientists who found the error are now telling us, in careful academic language, that the risk calculus has to be rebuilt from the ground down. So tonight we're going to do this properly. We will walk through why the old theory was invented, why it was actually a beautiful piece of reasoning, and exactly which measurements quietly broke it. We will meet the thing they found instead: a slow, continent-scale current of solid rock that the researchers call a mantle wind, driven by the ghost of a tectonic plate that vanished from the surface of the Earth millions of years ago. We will see how that wind melts rock without adding any heat at all, how it has torn a tilted seam through the plate you are living on, and why the famous lake of magma under Wyoming, the one from the disaster movies, turns out to have never existed. And then we will follow the system forward, because Yellowstone is not staying where it is. It has been moving for 17 million years, and there is something in its path. There is one more reason the timing of this study matters, and it is the reason some of you are watching tonight in the first place. The past 2 years at Yellowstone have been visibly strange at the surface. In July of 2024, a hydrothermal explosion at Biscuit Basin threw rock and boiling water hundreds of feet into the air and destroyed a boardwalk while visitors ran. This spring, the park logged a string of smaller steam-driven explosions. One of them caught live on a webcam in late April. In June, another blast opened fresh vents so close to a monitoring station that it became the best recorded event of its kind in history, and within days a brand new boiling pool had formed beside it, where solid ground used to be. We have covered every one of those events on this channel as they happened. None of them, I will say clearly now and again later, is a sign of rising magma. But they are the backdrop against which this new study landed, and they are the reason the question at the centre of tonight's video has an edge to it. When the ground is misbehaving and the experts announce that the engine underneath it is not the engine they thought it was, people deserve a careful, complete accounting of what that does and does not mean. It is also worth pausing on how rare this kind of reversal is. Science revises itself constantly at the margins. A date shifts, an estimate tightens, a mechanism gets a footnote. What almost never happens is a top-tier journal publishing a result that removes the central object from the diagram of one of the most intensely studied natural systems on Earth. That is not a margin. That is the load-bearing wall, and the fact that the new model was tested against 3 independent kinds of evidence: the seismic waves that pass through the region, the chemical fingerprint of the erupted rock, and the subtle variations in gravity that betray what is dense and what is not beneath the surface, is what separates this from a provocative idea. A wrong model can usually be made to fit one dataset. Fitting 3 at once, each measuring something different, is how you know you're looking at something real. But before any of that makes sense, we need to fix something more basic. Because most of what people think they know about Yellowstone is wrong from the very first sentence, starting with the assumption that there is a volcano there you could point a camera at. Part 2. The hole where a mountain should be. Yellowstone has no cone. When you picture a volcano, you picture a mountain, a steep-sided peak with a crater at the summit, something like Fuji or Rainier, or the pre-1980 profile of Mount St. Helens. Yellowstone offers nothing of the kind. There is no single mountain in the park you can point to and say, that is the volcano. And the reason is unsettling once it lands. The volcano is too big to see. Yellowstone is not a mountain. Yellowstone is a hole. The feature itself is a crater roughly 30 miles across in one direction and 45 in the other. Stand in the middle of it, and if you have visited the park, you have stood in the middle of it, and the rim is so far away that it sits at or beyond the horizon. You can photograph the elk, walk the boardwalks over the bubbling pools, drive for an hour, and never perceive that you are inside the mouth of anything. The crater does not read as a crater from ground level, it reads as terrain. Geologists call this kind of feature a caldera, and the word carries a specific and slightly horrifying meaning. A caldera is not blasted outward like a bomb crater. It is what remains when the ground collapses downward, when the roof of the system falls in because everything that was holding it up has left. The magma vacates, whether erupted into the sky or drained elsewhere, and the unsupported lid, hundreds of square miles of solid rock, simply drops. The hole in Wyoming is the signature of an evacuation. The system has done this on a grand scale 3 times in the past 2.1 million years. The first and largest event, about 2.08 million years ago, ejected something in the neighborhood of 2,450 cubic kilometers of rock, ash, and magma. A second, smaller caldera-forming eruption followed around 1.3 million years ago, at roughly 280 cubic kilometers. The third, about 630,000 years ago, produced the caldera the park sits in today and threw out on the order of 1,000 cubic kilometers. 2 of those 3 events crossed the threshold that earns a special designation. Anything over 1,000 cubic kilometers is called a super eruption, and it gets its own category because nothing else in the modern human experience compares to it. Numbers that large need an anchor, so here is the standard one. Mount St. Helens, May of 1980. The eruption that flattened 230 square miles of forest, killed 57 people, dropped ash across a dozen states, and dominated national news for weeks. Ejected about 1 cubic kilometer of material. 1. Yellowstone's most recent caldera-forming eruption was roughly 1,000 times larger. Its first was closer to 2,500 times larger. The event that seared itself into the memory of an entire American generation was, by this system's standards, a rounding error. Only about 20 places on Earth are considered capable of an eruption in the super-eruption class. We actually took a tour of that upper tier, and the even larger volcanic events beyond it, in our video from June 11th, so I will not rewalk that ground tonight. What matters here is why anyone loses sleep over the category at all. It is not the crater. Nobody is worried about a hole in Wyoming. The global concern is what a super-eruption puts into the sky. Enormous volumes of fine ash and sulfur compounds lofted into the upper atmosphere, where they spread, linger, and dim incoming sunlight. Global temperatures drop, not for weeks, but for years. Growing seasons shorten or fail, and a civilization that runs on just-in-time, food logistics does not have a plan for multiple consecutive failed harvests on more than one continent. That is the stake that makes the plumbing under Wyoming worth understanding correctly. It is worth spending a moment on what that collapse actually looks like, because the mechanics are part of why these systems are so hard to think about. In an ordinary eruption, pressure wins. Gas-laden magma forces its way up a conduit, and the mountain leaks or explodes at a point. In a caldera-forming eruption, the sequence inverts partway through. So much material evacuates the storage region so fast that the roof loses its support mid-eruption. Enormous ring-shaped fractures propagate around the perimeter, and the entire block of crust inside them, a slab of rock the size of a county, founders downward into the emptying space like a trapdoor. The fractures themselves become new vents. The eruption accelerates as the roof drops, and when it is over, there is no mountain to rebuild because there was never a single point of failure. There is a pit with a floor hundreds of meters lower than the ground that used to be there. The rock that came out does not pile up politely nearby either. It spreads as ground-hugging flows of incandescent ash that weld themselves into solid sheets over thousands of square miles, and the finer material goes up and comes down across most of a continent. Ash from Yellowstone's Big Three has been identified in deposits from the west coast to the Mississippi Valley and beyond. One system, in the middle of Wyoming, leaving its signature across the better part of the United States. The surface of the park today is the quiet version of all that history, though quiet is a relative term. Yellowstone hosts thousands of hydrothermal features, roughly half of all the geysers on Earth, along with the hot springs, mud pots, and steam vents that make the place worth visiting. And every one of them is a small vent on the same heat engine we're about to spend 2 acts rebuilding in your head. That hydrothermal system has its own violent moods, as the past 2 years have demonstrated, and as we will see in detail later tonight. For now, hold on to the essential point. Everything you can see and photograph at Yellowstone is surface expression. The machine is below, and the question of what the machine actually is turns out to have been open this whole time. If you want a taste of what even a modest version of that sky effect does to the world, history has already run the experiment. In 1815, Mount Tambora in Indonesia produced the largest eruption in recorded human history, an event far bigger than Mount St. Helens, yet still well short of Yellowstone's super-eruption class. The following year, 1816, became known across Europe and North America as the year without a summer. Frost struck New England in June. Crops failed across the northern hemisphere. Food prices spiked, and famine and unrest followed in multiple countries, all from a single eruption on the other side of the planet, an order of magnitude or more below what the system under Wyoming has done 3 times. That is the proper mental scale for the word super-eruption, and it is why the small community of scientists who study these systems care so much about getting the underlying machinery right. The difference between a correct model and a wrong one is not academic pride. It is whether the warning, if a warning ever comes, is understood in time to mean anything. And for 50 years we thought we did understand it. The explanation was elegant, intuitive, and taught to every geology student on the planet. It solved a puzzle that genuinely needed solving, because Yellowstone, on top of everything else that is strange about it, is in the wrong place, parked 1,000 miles from the nearest plate boundary, in a spot where, by the ordinary rules of volcanism, nothing should be erupting at all. The old theory explained that beautifully, which is exactly what made it so hard to kill. Part 3. The most beautiful wrong idea in geology. The old theory begins with a lava lamp. That is not a joke at the theory's expense. It is genuinely the best way to picture what geologists proposed was happening beneath Wyoming, and for decades it was a completely reasonable thing to propose. Heat the base of a lava lamp and watch what happens. A blob of warm wax at the bottom becomes buoyant, detaches, and rises through the cooler liquid around it in a slow, coherent column, barely mixing with its surroundings on the way up. Now scale that image to a planet. The bottom of the lamp is the boundary between Earth's molten outer core and the rocky mantle, nearly 3,000 kilometers beneath your feet, where temperatures approach those at the surface of the sun. The theory held that blobs of superheated rock detach from that boundary layer and rise, slowly, over tens of millions of years, as columns called mantle plumes. Where the head of a plume reaches the underside of a tectonic plate, it spreads out, melts, and burns through like a blowtorch held under a sheet of metal. The volcano at the surface is simply the scorch mark. The idea was proposed in its modern form in the early 1970s, and it solved real problems. Hawaii sits in the dead center of the Pacific Plate, thousands of kilometers from any boundary, and yet it erupts continuously. A stationary blowtorch beneath a moving plate explained not just the volcano but the entire chain of extinct islands trailing off to the northwest, each one a former scorch mark, carried away by the conveyor belt of the plate. It was elegant, it was intuitive, it made testable predictions, and when geologists went looking for other places to apply it, Yellowstone was the obvious candidate, because Yellowstone presents exactly the same puzzle in continental form. Think about where volcanoes are supposed to live. Nearly every eruption you have ever seen on the news happened at the edge of a tectonic plate. The Ring of Fire, the chain of volcanoes wrapping the Pacific from Chile up through Alaska and down through Japan to New Zealand, exists because oceanic plates are diving beneath their neighbours along those margins, carrying water down into hot rock and triggering melting. Iceland sits on a boundary where 2 plates are spreading apart. Volcanism is, overwhelmingly, an edge phenomenon. It is what happens where plates meet, grind, and consume one another. Yellowstone is nowhere near an edge. It sits in the interior of the North American plate, roughly 1,000 miles from the nearest plate boundary, surrounded by stable continental crust in every direction. By the ordinary rules of plate tectonics, there should be nothing there. No heat, no geysers, no calderas, just Wyoming. And yet the most productive explosive volcanic system on the continent sits exactly there, recharging and erupting on a repeating cycle stretching back millions of years. Something has to explain a furnace in the middle of nowhere, and a plume rising from the core mantle boundary explained it perfectly. The furnace was simply anchored beneath the plate, drawing on the deepest heat reservoir the planet has, indifferent to the surface geography above it. So the picture hardened into fact. The column went into the textbooks, then into the documentaries, then into the museum panels at the park itself. Generations of students learned Yellowstone as the type example of a continental hotspot, fed from the lowest mantle. Every animation you have ever watched of the supervolcano, the ominous red glow swelling beneath the park, inherited its geometry from that 1970s idea. And to be fair to everyone involved, the theory earned its status honestly. It explained the location. It explained the longevity. It explained the volcanic track across Idaho, which we will walk down later tonight, as the trail of a stationary torch beneath a drifting plate. The theory also came with a spectacular origin story for Yellowstone specifically, and it is one we have told on this channel before. Around 17 million years ago, the Pacific Northwest was resurfaced by one of the largest volcanic outpourings in the planet's recent history. The Columbia River flood basalts, layer upon layer of liquid rock stacking up until parts of Washington and Oregon lay under lava piles more than a mile thick. We spent a full video on eruptions of that class back on June 11th. In the classic plume narrative, that cataclysm was the arrival announcement, the moment the massive mushroom-shaped head of the new plume first reached the underside of North America and unloaded. The narrow tail behind the head then settled in for the long haul, and the chain of calderas marching toward Wyoming ever since was the tail's slow signature. One theory, two spectacular phenomena, a tidy timeline. When an idea explains that much with that little, it stops feeling like a hypothesis and starts feeling like scenery, something in the background of every other argument, no longer itself on trial. Yellowstone was not carrying this theory alone either, which raises the stakes of its failure. The planet hosts several dozen proposed hotspots, from Iceland to the Galapagos to Reunion, and for half a century the mantle plume has been the default explanation offered for nearly all of them, with the depth, vigour, and even existence of each individual plume perpetually under dispute. Yellowstone sat near the top of that list as the continental flagship, the example wheeled out first in every lecture, precisely because the alternative explanation seemed weakest there. 1,000 miles from a boundary, with a dated track behind it, if any hotspot needed a plume, surely this one did. Which is exactly why what the measurements began showing was so quietly destabilizing, and why the eventual verdict travels so far beyond Wyoming. If the flagship case never needed the column, every entry on the list is owed a fresh look. And the plume made one more elegant prediction that seemed for decades to seal the case: the track. If the torch is stationary and the plate drifts over it, then the line of dead calderas across Idaho should run exactly opposite to the direction of North America's motion, and it does. The plate creeps southwest a few centimeters per year. The volcanic scar marches northeast at the same pace. The geometry fits so cleanly that the Yellowstone track was used for years as a fixed reference point for measuring plate motion itself, a lighthouse assumed to be bolted to the deepest floor of the mantle. Keep that assumption in mind, because it is one of the quiet casualties of the new work. The track is real. The lighthouse is not bolted to anything. You could see how deeply it had embedded by looking at what got built on top of it. Hazard maps assumed the plume's heat budget. Petrologists interpreted the chemistry of Yellowstone lavas through the assumption of a lower mantle source. Documentaries, and I say this with some professional sympathy, rendered the column in glowing red for audiences who would carry that image for the rest of their lives. Even the skeptics mostly argued about the plume's details, not its existence, how hot, how wide, how tilted. A half-century of intellectual infrastructure, from peer-reviewed models to gift shop posters, stood on a single load-bearing assumption that had never actually been photographed. Nobody was being lazy or dishonest. The assumption was reasonable. It was just also, as it turns out, wrong. And the first cracks were already on record for anyone who looked at the measurements without the diagram in their head. But a scientific theory is not graded on elegance. It is graded on predictions, and the plume theory makes very specific ones. A rising thermal column is narrow, a focused pipe of excess heat, perhaps 100 or 200 kilometers across, small by planetary standards. It is vertical, or close to it, because buoyancy pulls straight up, and it is continuous, an unbroken thermal structure running from the core mantle boundary all the way to the base of the plate, like a pillar holding up a roof. Find the volcano, and the theory tells you exactly what should be underneath it. A hot, narrow, vertical anomaly, reaching down thousands of kilometers, glowing in whatever instrument you point at it. A dot on the map with a route going all the way down. For 50 years, that is what everyone assumed the instruments would eventually confirm once the instruments got good enough. The confirmation was treated as a formality, a matter of resolution, not of substance. The column was down there. Obviously it was down there. The only question was when someone would finally take a sharp enough picture of it. The pictures got sharper, and what they showed refused year after year to cooperate. Part 4. The evidence that refused to cooperate. Start with the shape of the heat, because that discrepancy is visible in data decades old. A blowtorch gives you a dot, a compact focused thermal anomaly centered under the volcano, fading out symmetrically in every direction. What the instruments actually measure under Yellowstone is nothing like a dot. The warm region is broad, it is lopsided, and most tellingly of all, it is tilted. The anomaly leans away from the park toward the southwest, spreading out under Idaho like a streak smeared across the page by a careless thumb. A vertical column does not produce a diagonal smear. For years, plume theorists patched the mismatch with auxiliary explanations. Perhaps the column was being bent by flow in the upper mantle. Perhaps the imaging was distorting a fundamentally vertical structure. The patches were never absurd. But notice what was happening. The theory had stopped predicting the data and started accommodating it. In science, that is the first quiet symptom of something terminal. The second symptom was worse, and it came from the tool that was supposed to deliver the triumphant confirmation. Seismic tomography is, in essence, a CT scan of the planet. Every significant earthquake anywhere on Earth sends waves through the interior, and those waves travel faster through cold, stiff rock and slower through hot, soft rock. Record enough earthquakes at enough stations, and you can reconstruct a three-dimensional map of where the interior is hot and where it is cold. The same mathematics a hospital scanner uses with X-rays, executed with earthquakes as the light source. Tomography is how we can see, with genuine confidence, the cold slabs of dead ocean floor hanging in the mantle beneath continents. The technique works. It finds things. It struggled, for decades, to find the one thing under Yellowstone it was supposed to find. A textbook plume, a continuous hot conduit from the core mantle boundary to the base of the plate, should appear in a good tomographic model as an unbroken bright column, thousands of kilometers tall. What the successive generations of models actually showed was ambiguity. Warm patches at some depths, gaps at others, candidate structures that appeared in one study, shifted position in the next, and dissolved in a third, tilting improbably as they went. Different research groups using different data and different methods kept producing different pictures of the supposed column, which is precisely what you expect when instruments strain to resolve something faint, and also precisely what you expect when the thing being resolved is not really there. The honest summary, whispered in seminar rooms far more often than it was printed in textbooks, the plume did not light up. Not clearly. Not the way a pillar of superheated rock reaching down to the core should. There were other lines of evidence, and in fairness some of them genuinely pointed the plume's way, which is part of why this debate ran for 2 decades in the open literature rather than ending in an afternoon. Yellowstone's gases, for instance, carry a measurable excess of a rare primordial form of helium, helium-3, that most researchers associate with material from very ancient, very undisturbed reservoirs in the planet's interior. For plume advocates, that chemistry was a signed letter from the lower mantle. The trouble is that chemistry of that kind tells you the material's ancestry, not its root or its depth of storage, and the new modelling shows shallow mantle flowing in from the side can carry old chemical signatures with it. The clue was real. The reading of it was not unique. The same pattern held for the heat itself. The park's measured heat output is enormous, dozens of times the continental average, an output that seemed to demand an extraordinary source. A pipe to the core answered that demand nicely. But so, it turns out, does a broad current of shallow hot rock delivered continuously from the side. Every major piece of pro-plume evidence had this character, perfectly consistent with the column and also, on closer inspection, consistent with something else. The imaging campaigns kept escalating too, which makes the ambiguity more damning rather than less. Through the 2000s and 2010s, an enormous scientific effort rolled a blanket of hundreds of portable seismometers across the entire continental United States, station by station, specifically to illuminate the mantle beneath North America at resolution nobody had achieved before. Yellowstone sat at the center of some of the most intense coverage on Earth. If a robust, continuous column of superheated rock connected the park to the core mantle boundary, the tools of the 2020s were the tools that should finally have pinned it to the wall. Instead, the sharpest pictures produced the least agreement. Some groups traced a faint, wandering warm structure descending at an angle and argued the plume was simply skinnier and more crooked than advertised. Others found the supposed conduit interrupted by cold material, including, tellingly, sinking fragments of an old oceanic plate parked squarely in the space the plume needed to pass through. Hold on to that detail. Those fragments of dead sea floor, lurking in the imaging like wreckage on a runway, are about to move from a complication in the old story to the engine of the new one. So by the early 2020s, Yellowstone science had settled into an uncomfortable posture. The plume theory still explained the two big facts: a volcano far from any plate edge and a track of dead calderas behind it, and no rival explanation was fully worked out. But the theory's two specific predictions, the narrow vertical anomaly and the continuous conduit to the core, had both effectively failed. The people closest to the data knew something was off with the standard description. You could find the doubt in review papers, hedged in careful language about unresolved structure and non-unique interpretations. What nobody could do was replace the picture, because replacing it required something that did not yet exist: the computing power and the modelling techniques to simulate the entire western half of North America, plate and flowing mantle together as one physical system, at high enough resolution to test the alternatives honestly. It should also be said, because it matters for how you weigh what came next, that the doubters were never silent. From the mid-2000s onward, a persistent minority of researchers argued in the open literature that the plume was a phantom and that Yellowstone could be explained by processes in the upper few hundred kilometers: plate stresses, shallow mantle circulation, the lingering disturbance left by an old subducted slab. They published, they held conferences, they were rebutted, and the argument ran for 20 years without a knockout blow in either direction, because neither side could compute its way to a decisive test. The reason I emphasize this is that when the resolution finally arrived this spring, it did not come as an ambush from outside the field. It came as the settlement of the field's own longest-running argument, and the winning side was the one that had spent 2 decades being told it was fighting the textbook. That is worth underlining, because it explains why a wrong picture survived so long at the most studied volcanic system on Earth. It did not survive because nobody looked. It survived because looking was not enough. The measurements could tell you the old answer had problems. They could not, on their own, tell you the new answer. Distinguishing a bent, faint plume from no plume at all requires building the alternative from first principles, constructing a virtual Western United States, letting real physics run, and seeing which underworld the physics actually produces. Until very recently, that computation was simply out of reach. In 2026, it stopped being out of reach. A team fed the machine everything we know about the region, and the machine handed back an underworld nobody had drawn. Part 5. The Machine They Built. Act 2 begins with a virtual continent. Everything so far has been about a picture that failed, a column that would not appear, measurements that leaned the wrong way, and a 50-year-old theory quietly running out of road. What happened next is that a research group at the Institute of Geology and Geophysics of the Chinese Academy of Sciences stopped trying to photograph the underworld and decided to grow one from scratch instead. Their tool was not a new telescope or a new seismometer. It was a simulation, and understanding what kind of simulation is the key to understanding why this result carries the weight it does. A geodynamic model is a physics engine for the inside of a planet. You divide a region of the Earth, in this case the entire western half of North America and the mantle beneath it, into millions of computational cells. Into each cell you load the best available data: the thickness and temperature of the crust, the age and structure of the plate, the density of the rock, the viscosity of each layer, the positions of known slabs and known warm regions from tomography. Then you impose the real forces. Plate motions push from the boundaries, gravity pulls on every gram of density contrast, heat flows from hot cells to cold ones, and then, this is the crucial part, you let go. You do not tell the model where the magma should be. You do not sketch a plume in and ask whether it survives. You let the equations of fluid dynamics and heat transport run, and the interior organizes itself according to physics, not according to anyone's favorite diagram. 2 layers do the interesting work in a model like this, and you need both names for the rest of tonight, so let me plant them properly. The lithosphere is the rigid outer shell of the planet, the crust plus the cold, stiff uppermost mantle welded to its underside. It is brittle. It breaks rather than flows. It is the thing we mean when we say tectonic plate, and beneath the western United States it varies wildly in thickness, thin and warm under the recently stretched terrain of Nevada and Utah, old and cold and profoundly thick under the ancient core of the continent to the east. Below the lithosphere lies the asthenosphere, and the asthenosphere is the layer your intuition is worst at. It is not liquid. It is not magma. It is solid rock that would look and feel like ordinary stone if you could hold a piece. But it is hot enough and pressurized enough that over geological time it flows, the way glacier ice flows, a solid that creeps. Give it 1,000,000 years and it behaves like a fluid. The plates float on it, and it circulates beneath them, and every important thing in tonight's story happens in the conversation between those 2 layers. What makes this particular model the most detailed of its kind is that it simulated both layers at once, coupled together at high resolution for the present day. Not a cartoon of a generic continent, but this continent, with its actual measured structure, its actual plate motions, its actual buried slabs. That coupling is computationally brutal, which is why nobody had done it at this fidelity before. It is also non-negotiable if you want the truth, because the plate and the mantle beneath it push on each other constantly. A model of one without the other is a model of a dance with one dancer missing. None of this makes the model infallible, and the researchers do not claim it is. A simulation inherits the uncertainties of its inputs. Plate thicknesses blur at depth, viscosity is imperfectly known, and any model of the mantle involves choices a different team might make differently. The paper's authority rests not on being beyond question, but on being the first account that explains the full pattern of observations without special pleading. No bent column patches, no unexplained smears. While surviving 3 independent tests, it could have failed. In science, that is what best available explanation means. It is a title held until somebody builds a better machine, and part of what makes this moment in Yellowstone research honest is that everyone involved says exactly that out loud. Then came the exam. A simulation, on its own, proves nothing. The interior it grows has to be checked against reality. The team laid their virtual continent alongside 3 independent kinds of measurement of the real one. Seismic imaging. Does the pattern of warm and cold rock in the model match the pattern the earthquake waves actually see? The chemistry of erupted rock. Does the depth and degree of melting in the model produce the compositions Yellowstone actually erupts? And gravity. Does the distribution of dense and light material in the model reproduce the subtle variations in the pull of gravity measured across the western United States? 3 data sets, 3 different physical quantities, 3 independent chances to fail. The model matched all of them. That triple agreement is the reason this paper landed in Science, and it is the reason the field is treating the result as a turning point rather than a provocation. It is worth being precise about what makes this approach different from everything that came before, because the distinction is the difference between drawing a suspect and running a lineup. Most of what we knew about the underside of North America came from inversion, working backward from measurements at the surface to infer what structure must be below. Inversion is powerful, but it is permanently haunted by a problem scientists call non-uniqueness. Many different underworlds can produce the same surface measurements, so the picture you reconstruct depends partly on the assumptions you feed in. That is exactly how a faint, ambiguous plume survived for decades. The data could not force a verdict. Forward modelling inverts the logic. You build the underworld first, from physics and independent structural data, and then ask what measurements it would produce at the surface. If the predictions match reality across multiple independent data types, your underworld has earned belief the hard way. The Yellowstone model was run forward. Nobody drew the answer into it. The answer grew. The scale of the computation deserves a sentence of respect too. Simulating a coupled plate and mantle system across half a continent means tracking temperature, stress, density, and flow through an enormous three-dimensional grid over and over until the system settles into the configuration the physics demands. A workload that lands squarely in supercomputer territory and that was genuinely impractical at this resolution even a decade ago. This is the sense in which the discovery is a child of computing power as much as of geology. The measurements that broke the plume had been sitting in the literature for years. What did not exist was the machine that could take those measurements and settle what they meant. One more feature of the design matters for trust. The model simulates the present day, a physics snapshot of the system as it exists now, not a speculative movie of the last 50 million years. That restraint is a strength. Reconstructing the ancient past multiplies unknowns, but the present is measurable. Today's plate thickness, today's slab positions, today's gravity field. By anchoring everything to the measurable present, the team gave their model the maximum possible number of ways to be caught in a lie. It was not caught, and having passed that exam, it could be interrogated about the one question that mattered, and the result stated plainly is this. The simulated Western United States produces Yellowstone. The heat, the melt, the location, even the tilted lopsided shape that broke the old theory, without any plume from the lower mantle at all, no column from the core mantle boundary, nothing rising from the abyss. The furnace assembled itself from ingredients that were already up here in the top few hundred kilometers, and the heat arrived moving horizontally. The model did not just fail to find the textbook picture, it generated the real measurements from a completely different machine, which meant the researchers could finally do what 50 years of speculation could not: point at the actual engine and name its parts. The first part they named is the strangest, because when you ask the model what carries the heat to Wyoming, the answer is that the rock under the western United States is not sitting still. It is blowing eastward, and it has been for millions of years. Part 6. The wind made of rock. There is a wind blowing under North America. The researchers chose that word deliberately. They call the phenomenon a mantle wind, and the choice is precise as long as you adjust your clock. In the model, and now presumably under your feet, the hot rock of the asthenosphere is not merely sitting beneath the plate waiting to be tapped. It is streaming, coherently and continuously, from west to east across the entire region. A broad horizontal current of solid flowing rock, sweeping beneath the western United States the way a weather system sweeps across the surface. The speed is geological, on the order of inches per year, comparable to the speed your fingernails grow. But scale is what makes it monstrous. This is not a draft in a corridor. It is a continent-wide river of rock, hundreds of kilometers thick, moving with a momentum measured in millions of years, and Yellowstone sits directly in its path. Slow does not mean weak. That current of creeping rock carries more thermal energy past any given line of longitude than every power plant humanity has ever built could move in centuries. When something that massive flows, even at fingernail speed, it reorganizes everything it touches. It drags on the underside of the plate, it piles heat against obstructions, it seeks and exploits weaknesses. Understand the wind and, as the model shows, you understand the volcano. But a wind needs a pressure gradient. Air does not move without a reason, and neither does the mantle. So what exactly has been pushing rock eastward beneath North America for all this time? The answer is the part of this story I've not been able to stop thinking about since April. The engine is a ghost. Go back in time with me about 150 million years. Off the west coast of North America there is an entire ocean plate that no longer exists in any atlas. The Farallon Plate, an immense slab of seafloor that once spanned much of the space between the Americas and the middle of the Pacific. As the Atlantic opened and North America drove westward, the Farallon Plate was consumed, forced down beneath the advancing continent, kilometre by kilometre, over more than 100 million years, until essentially nothing of it remained at the surface. A few coastal fragments, one of them the small plate whose subduction still feeds the Cascade volcanoes, a system we examined in our video from July 24th, are its only surviving descendants. In every map of the modern world the Farallon Plate is simply gone, but the mantle does not forget. A subducted plate does not evaporate when it leaves the surface. It keeps sinking, a cold, dense 1,000-kilometre sheet of dead ocean floor descending through the hot rock around it, like a sail of lead foil settling through honey. Seismic imaging, the same tomography that failed to find the plume, finds the Farallon with ease. Its wreckage hangs in the mantle beneath the central and eastern United States to this day, still identifiably slab-shaped, still colder than its surroundings, still sinking, and that is the engine. As the dead plate founders into the depths beneath the eastern half of the continent, it displaces mantle rock ahead of it and drags flow along behind it, setting up a slow, permanent circulation. And on the western side of that circulation, hot, shallow rock is pulled continuously eastward in under the high ground of the American West. The wake of the dead plate is the mantle wind. This is also, incidentally, not the Farallon plate's first starring role in American geology, and the previous one reshapes how you should hear this story. The standard explanation for why the Rocky Mountains exist at all, more than 1,000 kilometers from any coast, involves an episode late in the Farallon's life when the sinking slab went unusually flat, scraping along beneath the continent and transmitting stress far inland, crumpling the crust into ranges whose summits now hold the snow that feeds half the American West. The plate that built the Rockies while it was alive is, in the new model, the same plate that powers Yellowstone from beyond the grave. One piece of dead ocean floor, two of the most dramatic features on the continent, one raised by its descent, one ignited by its wake. Geology does not offer many stories with that kind of symmetry. The wind also quietly executes one of the oldest assumptions in the field, and I flagged this casualty earlier, the fixed hot spot. For decades, Yellowstone's track was treated as a stationary reference point, a lighthouse anchored in the lowest mantle, against which the drift of continents could be measured. But a wake is not an anchor. In the new picture, the melting zone is a moving weather feature. The interference pattern between a flowing current and a drifting plate, with no route in the depths and no obligation to hold still. The track across Idaho still exists because the pattern has been quasi-stable for millions of years. But quasi-stable is a very different promise from bolted down, and the difference matters enormously when we ask in the final act where this system is headed next. The lighthouse turns out to be a ship. I want to make sure the strangeness of this fully lands, because it is the emotional centre of the new picture. The old theory said Yellowstone was powered by the living core of the planet, a column of fire rooted at the boundary of the core itself, primordial and eternal. The new model says Yellowstone is powered by a corpse. The supervolcano is running on the momentum of a plate that died before the dinosaurs did, an ocean floor that no longer exists anywhere on the surface of the Earth, still stirring the interior tens of millions of years after its own burial. Wyoming's geysers are, in the most literal physical sense, haunted, animated by the settling of something long dead. There is no torch, there is a wake, and the forecast implications of being fed by a wake, as we will see, are radically different from the implications of standing over a torch. One clarification before we go further, because I know a portion of you are already composing the comment. This result is about Yellowstone, not about every hotspot on Earth. Hawaii's case for a genuine plume remains far stronger, an isolated column rising under the middle of an enormous ocean plate, with no buried slab wreckage nearby to offer a rival explanation, is a much cleaner candidate for the classic lava lamp picture. Mantle plumes as a phenomenon are almost certainly real somewhere on this planet. What the new work shows is that Yellowstone, the system that was promoted for 50 years as the great continental example of a plume, never needed one. Its location, its heat, its shape, and its history are fully explained by the machinery of its own neighbourhood, a dead plate, a flowing current, and a stressed lid. The type example turns out to be a case of mistaken identity, and that distinction cuts in an uncomfortable direction, because a plume, whatever its dangers, is at least steady, a fixed torch you can map and monitor. A wind-driven system is a system governed by shifting stresses, and stresses are harder to see, harder to model, and much harder to extrapolate. The model, of course, cares nothing for poetry, and its version of the statement is more useful. The source of Yellowstone's heat is not a fixed point below, but a moving current beside, hot asthenospheric material delivered horizontally from the west at shallow depth. And that reframing forces the question that the plume theory never had to answer carefully. A current of hot rock is still just hot rock, solid, creeping, unmelted. Hawaii-style plumes at least came with a built-in story for making magma, If Yellowstone's supply arrives sideways, already shallow, never having touched the lower mantle, what turns it from hot solid stone into the melt that feeds a supervolcano? The answer is a piece of physics that runs half the volcanism on this planet, and once you see it, you will never picture melting rock the same way again. Part 7. Melting without heat. Here is a question that sounds like a trick and is not. How do you melt rock without making it any hotter? Every intuition you have about melting comes from the kitchen. Butter in a pan, ice in a glass, metal in a forge. You add heat, the temperature climbs past a threshold, the solid becomes liquid. So when you hear that hot rock is flowing sideways beneath Yellowstone, the natural assumption is that somewhere along the way it gets hotter until it melts. That assumption is wrong, and the actual answer is the single most important piece of physics in this entire story. The rock under Yellowstone does not melt because something heats it. It melts because something releases it. Melting temperature is not a fixed number. It depends on pressure. Squeeze a material hard enough, and you can hold it solid at temperatures that would instantly liquefy it at the surface because pressure physically clamps the atoms into their crystal lattice and denies them the room to break loose. The rock of the asthenosphere lives in exactly that condition. At depths of 100 kilometers and more, it is hot enough that at surface pressure it would melt without hesitation, but it sits under the crushing weight of an entire column of overlying planet, and that weight keeps it locked in the solid state. The asthenosphere is not cool, it is imprisoned. Now let a parcel of that imprisoned rock rise. Not far, even a few tens of kilometers will do. As it rises, the column of rock above it shortens and the pressure on it drops, and here is the critical asymmetry. The pressure falls fast, but the heat has nowhere to go. Rock is a spectacular insulator, and a parcel the size of a city district cannot shed meaningful heat on any timescale shorter than millions of years. So the parcel arrives at shallower depth essentially as hot as it started, but with the clamp loosened. The melting threshold drops below the temperature the rock already has, and it begins to melt on the spot with not 1 degree of added heat. Geologists call this decompression melting, and if you remember nothing else from tonight, remember this mechanism, because it is the answer to the question we opened the act with. Nothing in the new model of Yellowstone adds heat to anything. The system creates magma by subtraction, by taking pressure away. The kitchen version, since one exists and it is a good one, a sealed can of soda, thoroughly warm. Nothing about it looks eventful. The carbon dioxide is fully dissolved, held in solution by nothing but the pressure inside the sealed can. Now crack the tab. You added no heat and no energy. You removed pressure, and the contents erupt into foam in under a second. The gas was always there. The drink was always ready. The only thing keeping it quiet was the seal. Rock at depth works the same way, with dissolved melt playing the role of dissolved gas, and this analogy is going to earn its keep twice more tonight, because as we will see, dissolved gas under a failing seal is also a fair description of the shallowest part of Yellowstone, and of the explosions the park has actually been producing for the past 2 years. This is not an exotic mechanism invented to rescue Yellowstone, and that matters for how much you should trust it. Decompression melting is the workhorse of terrestrial volcanism, arguably the single most productive melting process on the planet. The entire global mid-ocean ridge system, the tens of thousands of kilometers of volcanic seams that run down the middle of every ocean basin and continuously manufacture new seafloor, runs on rock rising passively and melting as the pressure comes off. Iceland runs on it. Most of the lava erupted on Earth in any given year owes its existence to pressure release, not to added heat. The mechanism is standard physics with a century of evidence behind it. What is new at Yellowstone is not the process. It is the geometry, where and why the rising happens. For completeness, there is a third way to melt rock, and knowing it exists sharpens why this one matters here. At subduction zones, the Cascades, Japan, the Andes, the descending ocean plate carries water bound into its minerals, and releasing that water into the hot mantle above acts like salt on an icy road. It chemically lowers the melting threshold, and magma forms without extra heat or reduced pressure. That is flux melting, and it is why volcanic arcs stand above every subduction zone on the Ring of Fire. So the planet has 3 melting recipes: add heat, remove pressure, or add water. The plume theory fed Yellowstone with the first. The new model feeds it with the second. And the difference is not bookkeeping. Each recipe stamps a chemical signature on the magma it makes, in the elements it concentrates and the isotopes it carries. That is precisely why the geochemical test in the model's exam had teeth. The rock Yellowstone has actually erupted, the team showed, is consistent with shallow decompression melt, the second recipe, rather than demanding a superheated delivery from the lowest mantle. The lava itself, sitting in outcrops geologists have sampled for a century, had been quietly testifying about its own origins all along. We simply lacked the framework to hear it. Because here is the subtlety. A horizontal wind, on its own, melts nothing. Rock streaming sideways at constant depth keeps its pressure and stays solid forever. To get magma out of a mantle wind, something has to force the flow upward, even slightly, and this is where the model produces its most counterintuitive detail. As the eastward current runs in beneath the western United States, it collides with the thick, cold root of the continent's ancient eastern core, the thick lithosphere we will meet properly in the final act. The flow is deflected, dragged, and locally pulled downward along the underside of that root, and the plate above responds by stretching vertically in exactly the way flowing water dimples and bulges around a boulder in a stream. In that zone of disturbance beneath the Yellowstone region, parcels of hot rock get levered upward through the pressure gradient, and they cross their melting threshold at remarkably shallow depth, near the very top of the asthenosphere, within a few tens of kilometers of the base of the plate. Not a chimney of melt rising from the abyss, a shallow churning zone where a sideways current, wrestling with the underside of the continent, wrings magma out of solid rock by decompression. Notice too what this shallow geometry does to the imaging problem that opened the act. It dissolves it. 50 years of searches failed to find a melt column in the lower mantle for the simplest of reasons. The action was never down there. All the essential machinery of the new model, the incoming warm current, the melting zone, the tear, operates in the top few hundred kilometers, exactly the depth range where tomography sees most clearly, and where, in hindsight, the data had been showing the lopsided, tilted, shallow, warm structure all along. The mystery was never that our instruments could not see Yellowstone's engine. They saw it decades ago. We were holding the picture at the wrong angle, looking through the shallow truth in search of a fiction beneath it. Stop and register what has happened to the geography of the threat. In the old picture, the furnace was thousands of kilometers down, at the boundary of the core itself, unimaginably remote, almost astronomical. In the new picture, the place where Yellowstone's magma is born sits within a few dozen kilometers of the base of the plate you live on. That is a lot closer to your feet than anyone ever drew it. The distance from the surface to the birthplace of Yellowstone's magma is less than the distance between two neighboring towns on an interstate. Closer, shallower, and produced by a mechanism that responds not to the slow thermal moods of the planet's interior, but to the shifting mechanical stresses of the plate itself. And that raises the last problem the new model has to solve, the one that stands between a pool of fresh melt and a supervolcano. Magma born at the base of the plate is still trapped beneath the plate. 60 or more kilometers of cold, rigid, brittle rock, the same lid that keeps the asthenosphere's heat politely underground everywhere else on the continent. Melt does not diffuse through a solid plate like ink through paper. It needs a pathway. It needs a floor. And the model says the same wind that makes the magma is also, slowly and violently, manufacturing its escape route. Part 8. The Tear. Take a slab of cold taffy and pull it from both ends. It does not snap like glass, and it does not stretch evenly like rubber. It thins in the middle. The material flows away from the center faster than it can be replenished. The cross-section narrows, and if you keep pulling, the thinned zone eventually fails and pulls apart along a seam. Now perform that experiment on a tectonic plate, over millions of years, and you have the second half of the new Yellowstone model. The half that answers the question the plume theory never answered well. Not where the magma comes from, but how it gets through 60 kilometers of solid rock to reach the surface, again and again, for 17 million years, in the same evolving corridor. The forces doing the pulling should be familiar by now, because they are the two characters of this act. From the west, the mantle wind, the ghost-driven current, presses eastward, dragging on the underside of the plate and shoving against the first major obstruction in its path. That obstruction is the second force's home, the ancient continental core to the east, whose lithosphere plunges far deeper than the young, thin, stretched plate of the Great Basin behind it. The wind piles into that cold root like current against a bridge piling. Meanwhile, the thinner western plate is warm and buoyant. It floats high, and its buoyancy generates a body force directed back toward the west. The result is a tug-of-war conducted through a single slab of rock, mantle flow pushing the sunken root eastward, buoyancy pulling the shallow plate westward, with the Yellowstone region caught precisely at the hinge. Caught between opposing forces, the lithosphere there does what the taffy does. It stretches, it thins, and along the axis of maximum strain it tears, not a clean break, but a zone of concentrated damage and necking, a corridor where the plate's cold underside has been drawn out, weakened, and breached. The model resolves this structure explicitly, and its geometry is the paper's quiet showpiece, a channel-like conduit cutting through the lithosphere beneath Yellowstone, and it is not vertical. It dips, leaning down toward the southwest, a tilted seam through the plate, like a knife wound delivered at an angle. You should be hearing an old detail click into place. The tilted, lopsided, southwest-leaning heat anomaly from Part 4, the smear that embarrassed the plume theory for decades, the shape that required patch after patch to reconcile with a vertical column, is not an embarrassment to this model. It is the prediction. Melt generated in the shallow asthenosphere feeds into the base of the tilted tear and ascends along it, plating the conduit's length with warmth. Map the heat, and you are simply tracing the wound. The single measurement the old theory could never digest is the single structure the new theory produces on its own, and that reversal, yesterday's anomaly becoming today's confirmation, is the classic signature of a paradigm actually turning over, as opposed to merely being challenged. The tier also explains Yellowstone's most underappreciated superpower, persistence. One eruption needs one batch of magma, but a hotspot that erupts, rebuilds, and erupts again across 17 million years needs a standing supply line, and a healed plate would cut that line. The model's answer is that the supply line is structural. The tear is not an event, it is a feature, held open by the same permanent tug-of-war that created it. As long as the ghost keeps sinking and the wind keeps blowing, the stresses that maintain the corridor keep operating, and fresh decompression melt keeps finding the same tilted staircase upward. The volcano is not a wound that keeps reopening by chance. It is a wound the planet is actively holding open. It helps to remember that the American West was already the stretched part of the continent long before anyone invoked ghosts and winds. The entire province between the Sierra Nevada and the Rockies, the basin and range, is crust that has been pulled apart for millions of years, broken into the parallel corrugations of mountain and valley that make the drive across Nevada feel infinite. Stretching is the region's default state, and the plate there is thin and warm compared to nearly anywhere else on the continent. What the new model adds is focus. The mantle wind and the buoyancy contrast do not invent extension from nothing. They take a region already predisposed to being pulled apart and concentrate the tearing along one specific corridor, the way a perforated line decides where a stressed sheet of paper gives way. Yellowstone sits at the perforation. The West made the weakness possible. The wind chose where it fails. One more consequence of the tear deserves a moment, because it quietly explains why Yellowstone's eruptions are so much more vicious than the mantle's raw product would suggest. The melt born by decompression at the base of the plate is basaltic, runny, relatively gas-poor, the same unhurried lava that builds Hawaii. Basalt on its own makes fountains and rivers, not continent-scarring explosions. But magma climbing a 60-kilometre tilted staircase through continental crust does not arrive unchanged. It stalls in the conduit's chambers and sills, cools, crystallizes in stages, and melts the silica-heavy continental rock around it, evolving step by step into rhyolite, a magma so thick and so gas-charged that when it finally fails, it does not pour, it detonates. The tear, in other words, is not just a passage, it is a refinery, converting the mantle's mild product into the most explosive material geology makes. The staircase is what turns a leak into a bomb. There is a philosophical inversion buried in that sentence, and it is worth pausing on because it reframes what kind of object Yellowstone is. Under the plume theory, the volcano was a point source, a place where something extraordinary from far below punched through an essentially passive plate. The plate was scenery, the plume was the actor. The new model swaps the roles. The heat supply is regional, broad, and in a sense unremarkable, a warm current that underlies much of the western United States. What is extraordinary is the plate, the one corridor where stress conspires to tear the lid open, and give that regional warmth a path. Yellowstone is not where the mantle is strongest. Yellowstone is where the lithosphere is weakest. The volcano is less a torch burning through the floor than a structural failure in the floor itself, and that distinction between a thermal object and a mechanical one is about to control everything we say about hazards, warnings, and the system's future. But before we can say any of it, there is one more piece of furniture from the old picture that has to be carried out of the room, and it is the biggest piece of all. Because everything I have described so far, the wind, the melting, the tear, happens below or within the base of the plate. We have not yet talked about what is actually sitting in the crust directly beneath the park. In the movie version, you already know. A colossal cavern of glowing liquid, the magma chamber, the lake of fire waiting for its cue. The new science has an answer about that lake, and the answer is the reason this video carries the title it does. Part 9. The Lake That Never Existed. There is no lake of fire under Yellowstone. I want to deliver that sentence without hedging, because it is one of the best supported conclusions in modern volcanology, and it still has not reached the public. The image everyone carries, the cavernous underground sea of glowing liquid magma, red and churning, waiting beneath the park like a loaded weapon, does not exist. It is not that the lake is smaller than people think, or deeper than people think, or quieter than people think. It is not there. And according to the accumulating evidence from Yellowstone and from every other supervolcano scientists have managed to examine closely, it never was. Not during the long quiet centuries anyway. The eras of Yellowstone's history when something like a lake of eruptible liquid actually existed beneath Wyoming may add up to a rounding error in 17 million years, which is either the most reassuring fact in this entire video or the most disturbing one, depending on which end of it you look at. We will look at both ends. What actually occupies the crust beneath the park is something geologists call a magma mush, and the name is chosen well. Picture wet sand just after a wave retreats, solid grains packed together, with water filling the gaps between them. Now make the grains crystals of cooling rock, and make the water molten magma, and you have the structure of Yellowstone's storage system, an enormous body of mostly solid crystals, with liquid melt distributed through the pore spaces between them. A slushy, not a soda. Estimates across recent studies put the melt fraction of the shallow reservoir at a modest slice of the total volume. The reservoir is, by any honest description, a hot solid with a liquid problem, not a liquid with a solid crust. And the mush extends far beyond the famous shallow reservoir. The modern picture, which the new study reinforces and finally explains, is a system of crystal-packed storage zones distributed through the whole thickness of the plate along the tilted conduit, from near the surface all the way down to the melt source, with no cavern, no void, and no lake anywhere in the stack. It is fair to ask how anyone can claim to know the texture of something buried miles beneath a national park, and the answer is the same physics that runs this whole story. Waves. Seismic waves do not merely reveal where rock is hot. Their speeds, and especially the behavior of shear waves, are exquisitely sensitive to liquid. Shear waves cannot pass through fluid at all, and they slow measurably when even a few % of melt threads the pore spaces of otherwise solid rock. Decades of increasingly refined surveys have sent waves through the Yellowstone Reservoir from every available angle, and the verdict has been consistent and unambiguous. The waves pass. They slow. They flag the region as hot and partially molten, but they pass, which no genuine lake of liquid would permit. The imaging shows a body that is overwhelmingly crystalline sponge, with melt occupying the minority of the volume, concentrated in pockets and lenses rather than pooled in a cavern. The lake was never hiding from our instruments. Our instruments have been politely reporting its absence for as long as they have been good enough to ask. The deeper architecture reinforces the point. Beneath the famous shallow reservoir, the rheolitic body a few kilometers down that stars in every documentary, imaging over the past decade has resolved a second, far larger storage region in the lower crust, a basaltic mush zone holding many times the shallow reservoir's volume, and below that the conduit continuing down toward the mantle source. Stacked storage, all of it crystal-dominated, all of it locked. And how do scientists know the eruptible liquid assembles late? Because erupted crystals are flight recorders. A crystal growing in magma lays down compositional layers like tree rings, and the chemical gradients between layers begin blurring by diffusion the moment they form. which means the sharpness of the preserved layers is a clock, recording how much time passed between a crystal's last growth spurt and the eruption that froze it. Researchers reading crystals from Yellowstone's past catastrophes and from similar super eruptions elsewhere keep finding the same unnerving answer: the final frantic phase of growth, the signature of the mush waking up and liquid organizing, spans decades to centuries at most before the end. Not geological time, historical time, grandparent to grandchild time. The mechanical consequences of mush are profound, and they carry the reassuring half of tonight's story. You cannot drain a slushy the way you pour a drink. Melt trapped in the pore spaces of a crystal framework is held there by the framework. It cannot slosh, it cannot surge, and above all it cannot evacuate quickly. The effective viscosity of a crystal mush runs orders of magnitude beyond that of liquid magma. Asking a mush to erupt is like asking a beach to flow through a keyhole. This is why the classic disaster movie scenario, something pokes the chamber and the lake comes roaring out, fails at the first step. There is no continuous liquid body to tap. An eruption from this system cannot simply happen. The system must first be transformed, reorganized from a locked crystalline sponge into something that can actually move. Yellowstone, in its present configuration, is not a loaded gun. It is a gun that has to assemble itself before it can fire. This revision also retroactively explains one of Yellowstone's most watched and most misread behaviors: the breathing. The caldera floor does not sit still. It rises and falls in slow cycles, accumulating centimeters per year of uplift for years at a stretch, then reversing into subsidence, a rhythm the GPS network has tracked through multiple episodes over recent decades, including a vigorous inflation pulse in the 2000s that generated a season of breathless headlines. Under the old model, every uplift episode invited the same dark reading: the chamber is filling. Under the mush picture, the readings are humbler and better supported. Pulses of magma or magmatic fluid entering the mush and rearranging, gas accumulating and escaping beneath the cap, the hydrothermal system inhaling and exhaling. The ground moves because the sponge shifts and breathes, not because a lake is rising toward a rim. Decades of these cycles have now come and gone without consequence, which under the old picture reads as a run of luck, and under the new one reads as a machine doing exactly what a locked venting mush should do. That, in miniature, is what a better model buys. The same data, stripped of a false alarm. So how does a mush ever erupt at all? Because it demonstrably does. The calderas are there, the ash sheets are there. 3 catastrophic proofs in 2.1 million years. The answer, supported by studies of the crystals erupted in past events at Yellowstone and at similar systems around the world, is that the liquid organizes, and it appears to do so shockingly late. Melt percolates slowly through the pore network of the mush over long spans of quiet. Then, in the run-up to an eruption, some combination of processes, fresh melt injection from below, gas accumulating under an impermeable roof, buoyant melt segregating out of the crystal framework, concentrates the distributed liquid into a genuine, connected, eruptible body of magma. The crystals record the timing, and the timing is the sting. The final assembly of eruptible liquid before a caldera-scale event seems to happen not over hundreds of thousands of years, but over timescales geologists describe as decades to centuries, in some crystal records, arguably less. The lake, when it exists at all, is a transient. It condenses out of the mush shortly before it is needed, does its unspeakable work, and is gone. Take a moment with the asymmetry of what that means, because the two halves of it are the hinge of this entire video. Half one, on any given day, today for instance, the absence of a lake means the system is fundamentally stable. The mush is locked. Nothing beneath Yellowstone right now is capable of producing a super eruption on any short timeline, and every researcher attached to this work says so plainly. Half two, the warning sign that 2 generations of us were taught to imagine, the great chamber slowly filling decade after decade, a rising gauge that instruments could watch climb toward red, is a picture of something that does not exist. You cannot watch the lake fill. There is no lake, and there is no gauge, and the thing that actually precedes an eruption is a late, fast phase change in a system that spends its whole life looking locked. And before you ask whether the instruments would see that phase change, hold the question. It is the right question. It is also the subject of part 12, because the honest answer needs 2 more pieces on the table first. The first of those pieces arrived in 2025, a year before the Mantle Wind paper, when a different team put a seismic flashlight on the very top of this system, the shallowest few kilometres under the park, and found the roof of the reservoir sitting closer to the boardwalks than almost anyone had drawn it, doing something nobody expected. Part 10. The Lid That Breathes. 2.4 miles. Take the walk from one end of a mid-sized airport terminal to the other, lay that distance straight down beneath the geyser basins of Yellowstone, and you arrive at the roof of the supervolcano's magma reservoir. 3.8 kilometres. That is the depth at which a research team announced in April of 2025 that they had located the sharp upper surface of the Yellowstone system, the definitive top of the storage region, using one of the most direct imaging experiments ever run in the park. Commercial aircraft cruise at nearly 3 times that height above your head. The top of the machine we have spent 9 parts rebuilding is closer to the tourists on the boardwalks than the boardwalks are to the nearest sizable city. The experiment deserves description, because its directness is what makes its results hard to argue with. Rather than waiting for earthquakes, the passive approach behind most of the imaging in this story, the team, drawn from Rice University, the University of New Mexico, the University of Utah, and the University of Texas at Dallas, brought their own earthquake source, a purpose-built vibration truck, essentially a machine that thumps the ground with precisely controlled force. They fired it hundreds of times along lines crossing the northeastern caldera, recording the reflections on a dense chain of hundreds of portable seismometers. It is the geophysical equivalent of switching from listening for distant thunder to shining a flashlight straight down, and the flashlight caught a boundary. At 3.8 kilometres, the reflections returned sharp and bright, revealing a distinct abrupt cap on top of the reservoir, not a gradual shading from solid rock into warm mush, but a definite surface, a lid with an edge. The composition of that lid is where the finding turns strange. Working through the physics of the reflections, the team concluded the cap layer is porous rock, holding roughly 14% open space in its structure, and that roughly half of that pore space is occupied not by melt, but by bubbles of supercritical water, water squeezed and heated past the point where liquid and steam remain distinguishable, mixed with silicate melt in the remainder. In the paper's language, it is a volatile, rich cap, a roof zone charged with pressurized gas, sitting on top of the mush like the head of foam on a poured beer, or, to reach back to part 7, like the gas dissolved and waiting inside a warm can of soda. A reader with a memory for this channel's coverage will feel a chill at that description, and the chill is legitimate. A shallow gas-charged lid is exactly the kind of structure that, sealed and pressurizing, precedes the violent steam explosions we have covered at other volcanoes. Gas accumulating under a cap is how systems load, which is why the second half of the finding is the half that matters most. The cap is not sealing. Everything in the data, and in the park's measurable exhalations, indicates the gas in that lid is escaping steadily upward, bleeding off through the fractured rock above it, and feeding the thousands of springs, geysers, and steam vents that make Yellowstone Yellowstone. The researchers' own image for it was a system breathing, pressure arriving from below, pressure leaking away above, a lid in dynamic balance rather than a lid winding tight. In their assessment, that steady venting is a signature of present-day stability. The release valve is open and flowing. The park's surface chaos, all that hissing and bubbling that reads to a visitor as barely contained fury, is better understood as the exact opposite, the visible proof that nothing is being contained. A Yellowstone gone silent, vents quieting, gas output falling, the ground swelling as pressure pooled under a healed seal, would be a Yellowstone worth losing sleep over. A Yellowstone that roars and steams from 10,000 orifices is a Yellowstone with its valve wide open. A word on why this cap went undetected through decades of world-class monitoring, because the answer restores some respect for everyone who missed it. Passive seismology, building images from distant earthquakes, is like mapping a dark room by the rumble of trucks on a highway outside. Superb for large structures, hopeless for sharp, thin, shallow ones. A cap a few hundred meters thick at 4 kilometers depth simply blurs into the background of that kind of image. Resolving it required bringing the light source inside the room, a controlled, repeatable, known signal fired at the surface directly above the target, which is expensive, disruptive, and logistically miserable in a protected national park, and therefore essentially never done. When the team finally did it, the The boundary appeared almost immediately, sharp enough that the researchers described the reflection as unmistakable. The lesson generalizes, and it is one of tonight's quiet refrains. The difference between there is nothing there and we have not looked properly is invisible until someone looks properly. It was true of the cap. It was true of the plume. It should hover over every confident sentence anyone utters about the inside of this planet. And what the light revealed deserves one more beat of appreciation, because supercritical water is not a substance most people have met. Squeeze water past about 220 times atmospheric pressure, while heating it past roughly 374 degrees Celsius, and it stops being either liquid or steam. It becomes a single phase with liquid's density, and gas's eagerness to expand, a fluid that flows like water but stores energy like a compressed spring. That is what half fills the pore space of the cap. It is superb at dissolving minerals, which is how it plugs and unplugs the fracture networks above it, and it is catastrophically responsive to pressure drops. Crack its container, and it flashes to steam with explosive violence, expanding its volume by orders of magnitude in an instant. Hold that image. A roof zone loaded with spring-loaded water, kept safe by the fact that its container leaks on purpose. The entire question of Yellowstone's day-to-day danger, as opposed to its million-year danger, lives in the health of that leak. Set this discovery beside the mantle windpaper, and notice what the pair of them did to our picture of this volcano in the space of about a year. In April of 2025, the top of the system moved. The reservoir's roof snapped into focus at 3.8 kilometers, shallower and sharper and more gas-charged than the standard picture had it. In April of 2026, the bottom of the system moved. The source dropped out of the lower mantle entirely and reorganized into a shallow, wind-fed, tilted tear. Both ends of the most studied volcano on Earth were redrawn within 12 months of each other, and in both cases the revision came not from new speculation but from new instruments and new computation finally outrunning old assumptions. Everything between the boardwalks and the core, in other words, is under active renovation, and the renovations keep agreeing on one theme. The system is shallower than we drew it, more structured than we drew it, and governed by seals, stresses and plumbing, rather than by the simple pressure gauge of a filling lake. There is one more reason the cap discovery belongs in this video rather than in a footnote, and it is a dark one. The cap sits at the depth where the story below and the surface story meet, where the magmatic system underneath hands its heat and gas upward into the hydrothermal system that tourists actually walk on. And the hydrothermal system over the past 2 years has been reminding everyone that it does not need any magma at all to hurt people. Because while the scientists were redrawing the depths, the surface of Yellowstone kept exploding, on camera, next to boardwalks, in front of families, and those events are the subject we turn to now. Part 11. 2 Restless Years. At 7 minutes past 10 on the morning of July 23, 2024, the ground beside Black Diamond Pool in Yellowstone's Biscuit Basin stopped negotiating. A column of steam, rock, and boiling mud tore out of the earth and climbed 400 to 600 feet into the summer sky, higher than a 40-story building, while chunks of debris the size of appliances rained down across an area of roughly a square kilometre. Families on the boardwalk close enough to feel the heat turned and ran as the wooden walkway behind them was smashed and buried under ejected rock. By the standards of what this channel usually covers, the event was small. By the standards of a family 20 metres away, it was the end of the world arriving without a single second of warning. No swarm of earthquakes beforehand, no alert, no siren. One moment a postcard, the next a detonation. Remarkably, no one was hurt. The basin was closed that day, and it has not fully reopened since. Long-time viewers know this event because we covered it, and we covered what came after, in our videos from May 18th and June 24th, as what came after kept coming. The park's hydrothermal system, having gotten our attention, declined to release it. Through this past spring, Yellowstone produced a run of roughly 5 hydrothermal explosions in 5 months. Small ones, mercifully, but a cadence that made even the professionals raise an eyebrow. One of them, on April 28th of this year, went off in daylight in front of a live webcam, giving the internet its first real-time look at the phenomenon. A sudden grey-white fountain erupting from placid ground, over in less than a minute. And then June 13th delivered the strangest chapter. At 9 minutes past 5 that morning, instruments registered a blast from barren ground just north of Black Diamond Pool, the same neighbourhood as 2024, that tore open a fresh line of vents along a 61-foot fracture, sent water at nearly 200 degrees Fahrenheit over the surrounding ground, and turned the Firehole River grey with suspended silica for 6 kilometres downstream. A monitoring station installed only the year before sat roughly 100 metres away, making this the closest scientifically recorded hydrothermal explosion in history, the first time the entire life cycle of such a blast was captured by professional instruments at point-blank range. And in the days that followed, the ground beside the new vents sagged, collapsed, and refilled itself as a brand new boiling pool, 21 feet by 17, which within a week was spouting water 20 to 30 feet into the air. A feature that did not exist on June 12th was, by June 18th, a permanent new resident of the park. Now, the responsible framing, and I will keep repeating it because it is true, none of this involves magma. A hydrothermal explosion is a shallow steam event. Groundwater percolating over the hot rock we have spent this video mapping gets superheated in the plumbing of the geyser basins. Silica dissolved in that water precipitates as it cools, and it gradually glazes the walls of the channels, narrowing and sealing them the way scale clogs an old kettle. Pressure builds behind the seal, and when anything perturbs the balance, a seasonal water table shift, a distant earthquake, or nothing detectable at all, the seal fails, the pressure drops, and the superheated water flashes instantaneously to steam, expanding hundreds of times over in a fraction of a second. It is the soda can again, third appearance, this time with the tab ripped off by force. The energy source is heat and gas from the magmatic system far below, but the explosion itself is pure plumbing failure in the top few dozen meters of the crust. The magma reservoir does not stir. The alert level does not move. Throughout everything I just described, both explosions, the spring run, the newborn pool, Yellowstone's official volcano alert status remained exactly where it has sat for years. Normal. Aviation code, green. So why give these events a full part in a video about the planet's interior? 2 reasons, and the first is proportion. This is the actual danger at Yellowstone, on any timescale a person plans a life around. The super eruption owns the nightmares, but the hazard with real, recent victims and real present odds is the hydrothermal system. The boardwalk scale blast that arrives unannounced in a park hosting 4 million people a year. The historical record around Yellowstone Lake includes explosion craters more than a mile across, blasted out by steam alone within the past 14,000 years, no magma required. That is the ceiling of this phenomenon, and the past 2 years demonstrate the floor is active right now. When we said back in May that the real Yellowstone threat is the ground and not the magma, this is what we meant, and nothing since has argued with us. For calibration, the park's own history offers a ladder of these events, and it is worth climbing quickly. The bottom rung is annual. Somewhere in Yellowstone, small hydrothermal bursts happen essentially every year, most of them unwitnessed in the backcountry, discovered afterward as a fresh apron of thrown rock around a reamed-out spring. The middle rung arrives every few years to decades. Events like the 1989 explosion of Porkchop Geyser at Norris, which blew its own throat apart in front of witnesses and scattered debris tens of meters, converting a named geyser into a simmering crater in a single afternoon. The upper rungs are the ones that reorder the map, explosions that excavate craters an acre and more across, recurring on timescales of centuries, and at the very top the events of the early post-glacial park, Mary Bay on Yellowstone Lake, a hydrothermal crater complex more than 1.5 miles across, torn out by steam roughly 13,800 years ago in what still ranks among the largest events of its kind known anywhere on Earth. Every rung of that ladder, top to bottom, was climbed without a drop of magma reaching the surface. The machine's smallest moods, expressed through nothing but hot water and bad plumbing, have historically been sufficient to destroy anything standing within a kilometre. There is also an honest scientific silver lining inside the June 13th event, and it belongs in the record. Having the entire explosion captured at 100 metres means researchers now possess, for the first time, a complete high-resolution recording of the phenomenon from ordinary background to detonation to aftermath. The exact data set needed to hunt for precursors more subtle than anything the human analysts flagged. If there is a tell buried in the final seconds, some whisper in the tremor band, some acoustic signature of a seal beginning to fail, that recording is where it will be found, and teams are actively mining it now. The first explosion forecast in history, if one ever exists, will likely trace its lineage to instruments that happen to be standing in the right 100 meters of Wyoming on a June morning. Until then, the operational reality for the park is unchanged and uncomfortable. The boardwalks cross a system whose smallest bombs give no notice, and the only mitigation is distance and luck. The second reason cuts to tonight's spine. Look at what the June 13th event proved about prediction. There sat a monitoring station 100 meters from the blast, close enough to record everything, the best seismic and acoustic data ever collected on a hydrothermal explosion, and in the reviewed data from the minutes and hours beforehand, researchers found no clear precursor, no warning shiver, no tell. The park's smallest explosions, it turns out, keep their counsel right up until the second they go, and these are the shallow, simple, well-instrumented events, the ones happening within shouting distance of the sensors. Hold that fact beside everything else tonight has assembled, because the surface has just taught us, twice in 2 years and once at point-blank range, the exact lesson the depths were about to teach us on paper. This system's failures are governed by seals and thresholds, not by smooth, watchable build-ups. Which brings us finally and unavoidably to the question this entire video exists to answer honestly. If the small blasts arrive without warning, what exactly do we think we would see before the big one? Part 12. The Warning Sign Problem. Every one of us was taught the same bedtime story about Yellowstone, and it goes like this. Yes, the supervolcano is terrifying, but we would see it coming. We would have decades of warning, probably centuries. The chamber would swell, the ground would rise, first by inches and then by meters. Earthquake swarms would rattle in crescendo for years. The instruments, all those seismometers, all those GPS stations, would watch the great gauge climb from green toward red with agonizing clarity. And there would be time to study, time to argue, time to plan, time to leave. The story is comforting. It is repeated by serious people in serious documentaries, and it rests, from its first word to its last, on the picture this video has been dismantling all night. The great liquid chamber that slowly fills. You cannot watch a lake fill if there is no lake. So tonight we have to update the bedtime story, carefully, honestly, and without flinching in either direction. Start with what a real, watchable magmatic warning looks like. Because one is happening right now, and we are lucky enough to have it as a control case. On Iceland's Reykjanes Peninsula, at a volcanic system called Svartsengi, scientists have spent the past several years doing precisely what the Yellowstone bedtime story imagines. A shallow body of magma sits beneath the area and refills on a rhythm the instruments read like sheet music. The ground above it inflates, millimeter by millimeter, day by day, as new magma arrives from below. The GPS network watches the swelling approach the level that preceded the last eruption. Scientists announce, sometimes within windows of days, that the system is primed again, and then fissures open, lava pours, the ground deflates, and the cycle restarts. They have called eruption after eruption this way. It is one of the great routine triumphs of modern volcano monitoring, and it works because Svartsengi is the textbook machine, a discrete, shallow, liquid magma body that genuinely fills and genuinely drains, with surface deformation as its faithful fuel gauge. That is the volcano the bedtime story was written about. Yellowstone, the new science says, is not that machine. There is no discrete liquid body quietly topping up on a schedule. There is a locked crystalline mush the size of a mountain range, breathing gas through an open valve, fed from a tilted tear by a current of solid rock. And the transformation that would precede a true eruption is not a filling, but a phase change. The late, relatively rapid organization of dispersed melt into a connected, eruptible body, a process the crystal records say plays out on timescales of decades or less, and which no scientist in history has ever observed happening anywhere, because no supervolcano has erupted in the era of instruments. Read that last clause again, because it is the honest core of tonight's video. Every confident statement about what the run-up to a super eruption looks like, including the comforting ones, including the terrifying ones, is an extrapolation from theory, from crystals, and from small volcanoes. The actual precursor sequence of a caldera-scale event has never been witnessed by anyone with a seismometer. We are, all of us, reasoning about the inside of a storm no one has ever flown through. Now, the two-sided truth, and I will give both sides their full weight. Side 1, this is not a no-warning scenario, and anyone who tells you Yellowstone could simply detonate out of a quiet Tuesday is wrong about the physics. Even a fast-assembling eruptible body must gather melt, move it, and force it through kilometers of brittle crust, and rock does not do those things silently. Melt migration on that scale generates earthquake swarms of escalating intensity, ground deformation beyond anything in the modern record, surging gas output, boiling changes across the hydrothermal system, signals qualitatively unlike the park's routine restlessness and the monitoring network, thousands of quakes catalogued per year, deformation tracked continuously, would register them. The machine cannot fire without assembling, and it cannot assemble in perfect silence. Side 2. The warning we would get is not the warning we were promised. The bedtime story offered centuries of stately, unambiguous build-up, a gauge. The revised picture offers something meaner, a system that spends millennia looking locked, whose transformation, when it begins, may run its course within a single human lifetime, and whose early signals would have to be distinguished in real time from the ordinary noise of the most restless geological province in America, a park where the ground already rises and falls in decade-long cycles, where swarms of hundreds of earthquakes already arrive and pass without consequence, where new boiling pools already appear overnight, none of it meaning anything. The nightmare is not silence followed by fire. The nightmare is a real signal, early in its life, looking exactly like a Tuesday. If you want to see this exact problem operating on a city instead of a park, look back at our July 14th video on Europe's most famous supervolcano. Campi Flegrei, the caldera holding 500,000 people in the western suburbs of Naples, is living the Yellowstone question in real time. Years of slow ground uplift, swarms of shallow earthquakes, a restless hydrothermal system prone to steam-driven violence, and an agonizing scientific debate over which signals, if any, mean magma and which mean plumbing. The Italian monitoring agency runs one of the densest networks on Earth there, and still the honest position is that nobody can say with confidence what the run-up to a real eruption would look like against the background of a caldera that is chronically, theatrically restless. That is not an indictment of the scientists. It is the nature of calderas, and Yellowstone is the same genus of problem with a thinner crowd and a bigger ceiling. The Mount St. Helens comparison from our July 24th video is the constructive half of the same lesson, because it shows what an unambiguous countdown actually looks like when a volcano deigns to provide one. In the spring of 1980, the mountain gave textbook notice. A swarm of escalating earthquakes, a visible bulge growing on its north flank at meters per day, fresh craters steaming at the summit, a signal so clear that authorities held an evacuation perimeter for weeks against furious public pressure. 57 people still died, many of them outside the official zone, and the eruption's opening move, a lateral blast out the side rather than a column out the top, was a shape almost no one had modelled. Even a volcano shouting its intentions through every instrument managed to kill, because the warning was legible only in hindsight's grammar. Now scale the ambiguity up. A system 1,000 times larger, whose warning grammar has never been heard by anyone, whose baseline behaviour already includes swarms, uplift, and explosions. The lesson of 1980 is not that warnings fail. It is that warnings arrive in a foreign language, and you learn the language either in advance, from correct models, or live at the worst possible moment. This, ultimately, is what the 2020 studies purchased, and why the researchers behind them describe the work in terms of rebuilt hazard models rather than raised alarm. Correct architecture is the prerequisite for a legible warning. A monitoring network watching for the wrong precursor is not neutral. It is actively misleading, a guard studying the wrong door. Moving the source from a bottomless plume to a stress-governed tier tells the seismologists which structures earthquakes carry meaning. Knowing storage is a mush that must connect before it can move tells the modelers which changes in the wave field would signal assembly beginning. Mapping the cap at 3.8 kilometers gives the gas geochemists a specific lid whose sealing, if it ever sealed, would now be recognized as the event it is. None of that existed a year and a half ago. All of it exists tonight. By any fair accounting, the park is better guarded now than at any moment in its history. Guarded for the first time by people holding an accurate diagram. What the diagram cost us is the bedtime story, and I think the trade was worth it. Comfort built on a wrong picture is not safety. It is just quiet. And that is why the reframing in these two studies matters practically and not just philosophically. The old model told monitors what to watch. The chamber, filling. The new model tells them the watch list was wrong. The load-bearing signals are elsewhere. How much melt is threading the mush, and is it connecting? Is the cap's release valve flowing, or beginning to seal? Is the deformation cycle just breathing, or has it stopped reversing? Those are subtler questions than watching a gauge, and some of them cannot yet be answered with existing instruments, which is, if you want tonight's takeaway in one sentence, the actual terrifying thing scientists are now saying about Yellowstone. Not that an eruption is near. Every researcher in this story states plainly that it is not. The mush is locked, the valve is open, the probabilities remain around 1 in 700,000 in any given year, the often quoted figure of roughly 0.00014%, and the popular claim that the system is overdue is a myth built on averaging 2 intervals, which is no average at all. The terrifying thing is smaller and sharper than doom. It is that when the people who watch this system for a living finally saw its true architecture, the warning sign they had been telling the rest of us to count on for 50 years was not in the picture. Part 13. The Trail of Dead Yellowstones. Open a satellite map of Idaho and you will see something that, once noticed, cannot be unnoticed. Cutting across the southern half of the state from the Nevada-Oregon border country in the southwest up to the mountain gates of Yellowstone in the northeast runs a corridor of improbably flat, improbably straight lowland, a smooth, dark, floored plain, 50 to 100 kilometers wide and several hundred long, curving gently like a scythe blade through terrain that is otherwise a chaos of ranges. Farmers grow potatoes on it. Interstate 84 rolls down the middle of it. It is called the Snake River Plain, and it is one of the most remarkable geological features in North America, because that lowland is a trail of corpses. Every stretch of that plain is the burial site of a caldera, a former Yellowstone that lived, erupted its catastrophes, and died, in sequence, one after another, as the melting zone and the continent slid past each other over 17 million years. The far southwestern end of the trail records the beginning, around 16 to 17 million years ago, in the border country where Nevada, Oregon, and Idaho meet. Caldera fields old enough that erosion and burial have reduced them to outlines only geologists can read. And the timing of that beginning is one of the old theory's proudest exhibits repurposed. It coincides with the Columbia River flood basalts, the continent drowning lava event we visited in our June 11th video. The Plume story read that as the arrival of the Great Column head from the core. The new model reads it as the moment the mantle winds melt, first found a viable tear in a freshly stretching plate, a different engine behind the same opening night. From there, the eruptive centers march northeast in a dated sequence as clean as tree rings, each volcanic field flaring into life, running through its cycle of super eruptions over 1 million years or two, then dying and subsiding as the plate carried it off the melting zone, its caldera sinking under lava flows and sediment to become another anonymous stretch of farmland. 12 million years ago, the fire was near Twin Falls, 10 million near Pocatello's latitude, 6 million approaching the Wyoming line. The plain is not metaphorically a graveyard. It is a literal sequence of graves, arranged in order of death, with the youngest grave still warm and the current resident, the living Yellowstone, sitting at the head of the line in Wyoming, its own 2 million year tenure already comparable to the full lifespans of several of its predecessors. The graves, it should be said, are not entirely cold. Drive the plain today, and the evidence of afterlife is everywhere once you know to look. At craters of the moon in southern Idaho, lava flows young enough to be nearly unweathered. The most recent, barely 2,000 years old, erupted well within human history. Sprawl in black fields across the corridor, the hotspot vacated millions of years ago, fed by the lingering warmth and lasting structural damage the passage left behind. The plain as a whole is still settling, still subsiding, still measurably warmer at depth than the ranges flanking it, a healing wound rather than an old scar. Geophysicists can trace the system's full biography in that corridor, the crust beneath the older sections growing progressively cooler, denser, and lower with age, sagging as the fires beneath them faded, the whole plain tilting through time like a cooling cake. It is one of the cleanest natural laboratories on Earth for a question that sounds like philosophy and is not. How long does it take a supervolcano to truly die? The answer written across Idaho, millions of years with relapses, is worth carrying into the final part, because we are about to ask what happens when the sequence of graves stops growing. Be precise about the motion, because the intuitive version is backward. The melting zone is not burrowing northeast through the continent. The continent is sliding southwest over the melting zone, at the few centimetres per year of plate motion. The melt source stays roughly put, in the mantle's reference frame, while North America drags itself across the flame like a sheet of paper, pulled slowly over a candle. The scorch line grows at the trailing edge. That is why the calderas get younger toward Yellowstone, and it is why the system's future address is predictable in direction even under the new model. As the plate continues southwest, the active zone's position on the map continues its slow march northeast, out of the park's northeast corner and onward, at roughly the pace fingernails grow, a couple of caldera lifetimes per state. Counting the graves is its own sobering exercise. The corridor holds not one or two predecessors, but a sequence of major volcanic fields, half a dozen and more distinct caldera centers that geologists have named and dated, several of which individually produced multiple super-eruption-class events during their reigns. The tally of caldera forming eruptions along the full 17 million-year track runs well into the dozens, which quietly reframes the living system's statistics. Yellowstone's 3 caldera events are not a complete biography, but the newest page of a much longer ledger. Reading the older pages takes work. The dead calderas do not present as craters, but as buried structure, resolved through drill cores, gravity surveys, and the fingerprinting of far-flung ash layers, each welded sheet matched to its source like shrapnel traced to a shell. The completeness of that record is also its warning. Nothing about the ledger suggests the phenomenon ends on its own. Every previous field died only because the plate carried it off the flame. What finally stops the sequence, if anything does, has to be something new in the system's path, which is precisely what now stands in its path. Here is what the new model changes about this old story, and it is subtle but consequential. Under the plume theory, the track's future was guaranteed. The torch is anchored at the core, the plate will keep moving, therefore new Yellowstones will keep igniting to the northeast forever, as inevitable as sunrise. The lighthouse promised it. But we established in Part 6 that the lighthouse is a ship. The melting zone is a stress pattern, an interference feature between wind, tear, and plate, with no anchor below and no guarantee attached. A stress pattern persists only as long as its causes persist and its conditions allow. For 17 million years, conditions have allowed, because the system has been chewing through the accommodating crust of the stretched, warm, thin American West, a soft target, mechanically primed for tearing, offering the wind an easy seam every step of the way. Look northeast of Yellowstone now, though. Look at where the trail's arithmetic says the next graves should go, and the map stops cooperating. The soft country ends. Everything about the terrain ahead is different. Older, colder, harder, and profoundly thicker. The system that has spent its entire existence tearing through the continent's weak flank is, for the first time in 17 million years, pointed directly at the continent's armour. Part 14. The Wall Ahead. Every continent has a core of old iron, and North America's lies directly in Yellowstone's path. Geologists call it the Wyoming Craton, one of the ancient nuclei around which the continent originally assembled, a block of crust and welded-on mantle root that has survived, rigid and cold and essentially unbroken, for more than 2.5 billion years. Cratons are the closest thing plate tectonics has to permanence. Their lithosphere extends far thicker than the young stretched plate of the Great Basin, a cold keel reaching down on the order of 200 kilometres, twice and 3 times the thickness of the terrain the hotspot has been tearing through. And their strength is the reason they still exist at all, having shrugged off billions of years of collisions, rifts and passing storms in the mantle beneath them. The Snake River Plain records what happens when this volcanic system meets soft crust. Nothing on Earth records what happens when it meets a craton, because in 17 million years it never has. That meeting is now geologically imminent, underway, arguably already. The northeastern edge of the active system is pressing into the transitional country, where the thin west ends and the old continent begins. One essential honesty note belongs here, before the two futures, because the word eruption has been doing heavy lifting all night. Nothing about the wall ahead, or the mush behind, forbids Yellowstone from erupting in its ordinary register, and its ordinary register is not the apocalypse. In the 630,000 years since the last caldera collapse, the system has produced dozens of lava eruptions inside and around the caldera, thick, slow, rhyolite flows, the youngest of them the Pitchstone Plateau flow at roughly 70,000 years ago, events that would rank among the largest volcanic spectacles in American history if one occurred tomorrow, and that would threaten almost no one, because flows of that kind advance at strolling pace, and the park would empty long before the lava reached a boundary. An eruption of that class remains far and away the most probable next act whenever the system next performs at all, orders of magnitude likelier than a caldera event. The super-eruption is the ceiling of this system, not its habit, and every probability in this video, small as it already is, shrinks further once you remember that most of what even an active Yellowstone does is not the thing the documentaries are about. The physics allows two futures, and they are not mildly different. They are opposites, and the new study is honest enough to leave both standing. Future 1, the wall wins, and Yellowstone dies. A craton keel is not just thick, it is cold, and it hangs down into exactly the shallow layer where the mantle wind delivers its heat and brews its melt by decompression. Push the melting zone under that keel and every term in the equation degrades at once. The wind must dive deeper, raising the pressure clamp instead of releasing it. The vertical stretching that levers rock upward is resisted by a lid too strong to neck and tear. The heat that once concentrated into a tilted seam instead spreads, diluted, along the underside of an unbreakable floor. In this future, the system that outlived 17 million years and a dozen incarnations simply starves. The eruptions space out, weaken, and stop. The last caldera cools into the last grave, the geysers gutter out over some tens of thousands of years, and the Yellowstone hotspot ends, smothered under the armor of the old continent, its trail across Idaho left behind as the complete and final biography of a dead phenomenon. Future 2. The wall does not win cleanly, and this is the future that keeps the careful language in these papers so carefully worded. Because a lid, as this video keeps discovering at every scale from soda cans to steam explosions, has two functions. It suppresses and it stores. If the wind keeps delivering heat that can no longer vent through easy, frequent eruptions, if melt continues to be generated more slowly at the craton's soft edges while the escape routes above have sealed, if the tear, rather than dying, hangs at the boundary and lets pressure and melt accumulate against the wall on timescales with no precedent in the system's history, then the craton is not a smothering blanket. It is the strongest container this volcano has ever been asked to test, and the one unbreakable rule running through every act of tonight's story, from the warm can of soda to the silica-sealed springs of Biscuit Basin to the volatile cap breathing at 3.8 kilometers, is that contained systems do not fail gently in proportion to their containment. The stronger the seal, the longer the quiet, and the worse the day the seal loses. Which future is ours? Nobody knows. The models cannot yet say. The researchers, pressed, decline to guess, and the timescales are mercifully immense. The collision unfolds across hundreds of thousands to millions of years, and no human alive, nor any human civilization we can meaningfully imagine, is likely to attend the answer. But it is worth sitting for a moment with the strangeness of the fact itself. The question of how the most famous volcano on Earth ultimately dies, quietly starved or catastrophically contained, was not even askable 18 months ago, because we had the engine wrong, and you cannot forecast the death of a machine you have misdrawn. Before we land this, let me spend a minute on the corners of the internet, because a story like this one gets metabolized badly, and some of you will meet the bad versions this week. You will see claims that this study is preparation, that the agencies know an eruption is near, and the no-warning framing is how they soften us up. Walk through why that fails on its own evidence. Everything in the new work points toward a system that is harder to erupt than previously believed, not easier. A locked mush, an open valve, no assembled eruptible body. The monitoring data underpinning that assessment streams into public archives in real time, where any graduate student on Earth can audit it. And the study itself is the proof that this scientific community publishes its inconvenient reversals in the open, because publishing inconvenient reversals in the open is precisely what it just did, in the most visible journal it could find. A conspiracy that announces its own corrections on the front page is not a conspiracy. It is just science, working. You will see claims that there will be no warning means they will never tell us. We spent part 12 on the honest version. The promised warning, the filling chamber, was a fiction of the old model, but physics has not gone anywhere. Magma cannot assemble and climb through a plate without shaking it, and the revised watch list exists precisely so those signals get read correctly. And you will see claims that outside scientists exposed what American agencies hid. The record says otherwise. The plume's failures were documented for 2 decades in open, largely American literature. The observatory's own researchers helped build the case that the old picture was failing, and the new model was published jointly with and validated against data the American monitoring system spent 50 years collecting and sharing freely. Nobody hid anything. The truth is less cinematic and more humbling. Everyone, everywhere, was honestly wrong together until the tools got good enough to be right. And that is the real ending of tonight's story. Not a date, not a threat, but a mirror. Yellowstone did not change this year. The mush is exactly as locked tonight as it was 2 years ago. The wind has been blowing for tens of millions of years. The ghost of the Farallon has been sinking since before our species' first ancestor stood upright. The odds of catastrophe tomorrow remain, by every serious estimate, vanishingly small. What changed is the picture in our heads, and the discovery worth losing a little sleep over is not the volcano at all, but the 50-year gap between confidence and truth. The most studied, most monitored, most photographed volcanic system on this planet, a place with its own federal observatory, wired with instruments for half a century, described in 10,000 papers, had the direction of its own heat supply wrong. Up, we said. Sideways it was. Every map of the planet's interior is like this, not a photograph but an inference, assembled from wave shadows and gravity whispers and mathematics, provisional in ways the confident diagrams never admit. Tonight, somewhere under Wyoming, solid rock is creeping eastward at the speed your fingernails grow, melting as the pressure lifts, pooling into a tilted seam that feeds a sleeping crystal sponge the size of a mountain range. And that sentence, the truest one available, is younger than the shoes you're wearing. What else, in the diagrams we have not yet had the tools to check, is drawn just as confidently and just as wrong? Here is the thread to pull next, and it is already being pulled. The mantle wind model makes predictions, specific checkable predictions about where the warm rock sits, how the tear is shaped, and what the next generation of seismic arrays should see when they stare into the space where the plume was supposed to be. Independent teams with independent tools are aiming at exactly that space now, hunting the confirming image or the contradicting one, and whichever arrives first will be the next chapter of this story. When it lands, you will hear about it here on the Nightwatch. Because the deepest lesson of the past 18 months is that this system rewards exactly one behavior: watching. And somewhere in the data streaming out of Wyoming tonight, the next wrong diagram is already failing quietly, waiting for someone to notice.